Chapter 4 is all about quantitative data. We're going to look at the different types of displays for quantitative data and also how to summarize that type of data. So let's take a look at our first type of graph. This would be the most common graph used for category or for quantitative data, and that's a histogram. A histogram is a graph that uses bars to show how many data values lie between each range of numbers. Now, these graphs are used specifically for very large quantities of data and a very large range of data. So when you have thousands of data values where it would make it very difficult to graph each individual data value, that's when a histogram is used. Now, there is a big downfall to a histogram. These graphs don't show each individual data value. And I'll explain by looking at the graph. Over here, we have an x-axis. The x-axis shows the scores on a final exam. So obviously, we have a scale here, 0, 20, 40, 60, 80, and 100. So let's just take this red bar right here. Its boundaries are 0 to 20. So all we know is that if we come over here, that's maybe, let's estimate 4 people, 3 people, 4 people. All we can say is that 3 or 4 students, because the y-axis is the number of students, all that we can say is 3 to 4 students scored between a 0 and a 20. This yellow bar, it looks like it hits right at about 20. The best we can say is that 20 students scored between a 40 and a 60. We don't know their actual scores, so that's the downfall to histogram. You don't know every individual data value. Now, there is one important thing for a histogram that makes it not a bar graph, and that is the bars must touch. If you have any gaps, you are not making a histogram, because one important thing about a histogram, this scale on the x-axis, it's continuous. There is no breaks in it. It goes from 0 to 20 to 40. The only reason that you would have a blank on this graph is if there was no data values in that region. So if nobody scored, say for instance, between a 20 and a 40, this bar would not be there and you would have a gap. But that's the only reason you would have a gap on a histogram. So let's look at some more information about a histogram. So histograms, there's a couple of important pieces. The next vocab word is a pile. A pile is simply another name for each one of the bars. You think about it, when you create a pile, you go up, so the bars go up. Bins. This is the groupings of the data on the x-axis. So on the graph we were looking at, the bins would be 0 to 20. The next bin would be 20 to 40. It's how wide each of the groupings are. And one important thing, the bins must always be the same width. So the bins and the counts in each bin give the distribution of the variable. So it tells us how many are in each region. The piles, which were the bars again, as I said, they touch on a histogram because all numbers are included. And a gap, the only reason that there would be a gap is if that bin is empty. Now, we've seen this word relative before. The last time we saw the word relative, and it's the exact same reason, the word relative, frequency histogram, relative always means percentage. So this displays the percentage of cases in each bin instead of the count. So the only difference, this talks about relative frequency. In other words, these are the percentages. So 50 to 100 falls right about there. That would be maybe 0.08. I'm sorry, 0.08. So that would represent about 8%. This bar right here goes to, I don't know, about 0.17 or 17%. So it's just showing the percentage of the whole in each pile instead of the individual counts. Now, look at the important information. How do we make a histogram? So the first thing we do is we need to divide the data up into even bin widths. Now we prefer typically 5 to 7 bins. So I do have a little trick because this is, the hardest part. Where do I start? So to find how wide to make the bins, take your range, which if you remember is your high minus your low, and divide it by 6. Now, this might very well give you a decimal. I'm not expecting you to use a decimal for how wide to make your bins. You can round up or down to the closest whole number. You could even, if it comes out to 7.8, you can round it to 10, and that's acceptable. This is just giving you a rough idea. So that'll give you an idea as to how wide to make each bin. Then you have to figure out a starting value to label your x-axis with. Well, you have to cover the entire range of data. So your starting value would definitely need to be less than or equal to your smallest value. If your smallest value is a random number like 7, you don't need to start at 7, you can start at 5. Or you can even start at 0. It just depends upon how big your data is. These are the numbers that you're going to have to play around with a little. Decide where to start, count by that bin width, and see if you fall at a decent ending place. So don't go making your x-axis with pen. Write out a list on your paper. Don't go straight to the graph. You might have to mess around a little bit with this. But once you've decided where to start and you know how wide to make each one of your bins, use a ruler so that everything is evenly spaced and make a mark for the start and the end of each bin and label those numbers. And remember, you have to have a consistent scale. Then count the number of data values that fall into each bin. Then go and create your y-axis, again using an even, appropriate scale to display the counts. If your highest count is 5, don't make your scale go up to 20. Make it go 1, 2, 3, 4, 5. If your highest count is 20, count by 2s, 2, 4, 6, 8, or count by 3s. But if your highest number is 20, don't count by 5s. The more numbers you can have on your scale, the easier it is to read your graph. And again, use a ruler to create your y-axis so that everything's evenly spaced. And then again, use a ruler to draw each one of your bars because everything needs to be nice and neat and clean. And finally, don't forget to include your labels on your x and your y-axis. Now this is the most difficult graph, and we will go through one in class together so that you have a chance to see kind of my thought process, and I think it'll make it a little easier for you to understand. So now let's get into the graphs that you're probably more familiar with. Stem and leaf display. I'm sure you've probably made one of these in Algebra 1. These are graphs that show the distribution of quantitative data, but the nice thing is, unlike a histogram, these you see all of the individual data values. These graphs are used for a smaller quantity of data, but they still can be used for a large range of data. And your leaf numbers must line up in columns. So your stem is always your your stem is always your first digits. And your leaf is always your last digit. That's an important thing. Your leaves can never be more than 1 digit. So if your stem can be, but your leaves cannot. So if it's a decimal, if it's something like 3.75, you're going to have to get rid of this 5. You can only use the 7. And notice these are columns. If these are not in columns, you will lose points. These have to line up because then you're able to see which area has the most data. And as you can see, that guy right there, these single digits, those are your most common digits. And then the other thing that's important is your key. You have to tell the reader whether to read these as whole numbers or decimals. 6-3 in this case is 63. If I wanted to make a key for this guy right here, I would say 3-7 equals 3.7, and that's perfectly acceptable as well. So let's look at how to construct one of these. Cut each data value into its leading digits, which again are your stems, and the trailing digits, which are your leaves. The stems always go on the left. As I just got through saying, use only one digit for each leaf. You can either round or truncate, that means cut off the data values to one decimal place. And one important thing, they must be in order from low to high. If they're not in order, you can't really graph it accurately. Now let's look at another one that should be familiar to you. These are called a dot plot. These are the easiest ones in my opinion to make. These are the simplest display. And all you have to do is place a dot or an X along an axis for each case in the data. You must count by ones along your x-axis. So notice here along the x-axis, we're counting by ones. 45, 46, 47, 48, 49, 50, 51, and this would be 52. You don't have to start at 0. I started at 45 because that was the first data value. Start wherever you need, but once you start counting, you have to count every number. Notice 46, there's nothing there, but you have to have it to represent that spot in the scale. And then each one of these dots represents a data value. And again, you may have seen them with X's before. You may see X's here building up instead of dots. If you like X's, by all means make X's. And these graphs are used for very small quantities and small ranges of data. Now, one important thing, just like stem and leaves, notice these dots line up across from each other. These have got to be the same size. They have to be lined up nice and even so that you can tell which graph has the most or which number is the most common. And in that case, that would be 50 right here. 50 was the most common data value because everything's lined up nice and even. So how do we make a dot plot? Well, first you have to draw an axis. Using a ruler, you have to count by a nice consistent scale of 1. Remember I said you can start wherever you want though. Then simply place a dot or an X in the appropriate location for each data value. With multiples of the same data value, you build the piles up by putting dots or X's above each other. And again, make sure you keep those dots the same size and height so you can easily see the height of each pile. All right, one last graph that we need to discuss, and that is a box plot. This one you may or may not have made before. A box plot is a graph that focuses specifically on the median, the quartiles, and the spread, which is your maximum and minimum. So this is that 5-number summary that we've talked about before. So the 5-number summary. These graphs can show data values that are considered outliers. Those are ones that are either really, really big or really, really small and don't belong. Now, just like a histogram, these graphs do not show all of the data values. So the important pieces, this guy right here, this is your minimum. It's your lowest data value. This mark right here, this is your Q1 that we've talked about. The line in the middle of the box is your median that we've talked about. The other edge of the box is your Q3. And this final end of a whisker right there, that's your maximum. So how do we make a box plot? Well, the first thing you need to do is calculate the 5-number summary the way we learned earlier. You need to find your maximum, minimum, median, lower quartile, and upper quartile. Then you need to draw an axis with a consistent scale that covers the full range of the data. If your minimum is 30, You don't have to start at 0, you can start at 30, but that scale has to be consistent. Count by 5s, count by 10s, count by 2s. It all depends upon how wide the range of data is. Once you have your axis, then you draw your box. So the median is the middle line in the box, and then your Q1 and your Q3 are the other ends of the boxes. Use a ruler, of course, and draw the top and the bottom of the box. Once you've made your box, then draw your whiskers. One whisker goes out to the maximum from the right side of the box, and your other whisker goes from the left side of the box down to the minimum. Now, you're going to be working on all of these in class. The other piece of information that we need to talk about today are the different shapes that you can have in these graphs. So we know what a mode is. A mode is a number that, of course, occurs the most. In a graph, modes are your humps. So a graph that is unimodal, uni means one, simply has one main peak in the graph. A graph that is bimodal, bi means like a bicycle, two. This is a histogram that has two peaks throughout the graph. And then multimodal simply means a histogram with 3 or more peaks. We don't have any other fancy names other than multimodal. Now, if you have a graph that doesn't look to really have any peaks, it's kind of flat most of the way, uniform means things look the same. People who wear uniforms to work, they look the same. Uniform is a histogram that doesn't appear to have any modes. In other words, all the bars are approximately the same height. So let's take a look at these two graphs. This first one, notice they're not perfect, but a lot of those bars are kind of right around the same amount. There isn't any major dips. This first example, this would be an example of uniform because they're mostly the same. This graph, notice there's two peaks in it. It goes up and comes down and goes up and comes back down. Two peaks, two means bi, so this is bimodal. Simple as that. There's other ways to describe the graphs other than their humps. Hopefully you've heard the word symmetrical before. Symmetry means that something looks the same. Symmetrical is simply a histogram where you can fold the histogram along a vertical line through the middle and have the edges match up pretty closely. So this graph, notice there's a little dashed line going down the middle right here. If we take and fold that graph over, if you notice, things line up pretty evenly. Are they perfect? No, they don't have to be. They just need to kind of look the same. The other type of shape is that has a tail on it. A tail is the thinner end of a distribution. It's where it gets flat and skinny and low at the bottom. This is what's referred to as skewed. Skewed is a histogram where one tail stretches out further than the other. So, and we use specifically the words skewed right or skewed left. So it's skewed to the side of the longer tail. So if you look at example 3, this graph, there's a tail here, whereas this side doesn't really have a tail. This tail means that this one is skewed left. Whereas this one goes up and then it's got this long tail over here. This would be skewed right because the tail is on the right. So whichever side the tail is on is the direction that it is skewed. And then we've already mentioned, I mentioned outliers briefly. Outliers are stragglers that stand off away from the rest of the body of the distribution. You look at this graph, all of the graph is right here, except for this little loner bar. That loner bar, that would be considered an outlier. He's a random bar that doesn't really fit with the rest of them. And so that's the idea of an outlier. So when you get to class, I'm going to have another graph packet for you to work on, and we will go through a histogram together so that you feel confident with those.